So let's talk about and reorient yourself with the slice diagram here, and we're just going to talk about this upper area here in that darkest gray-brown color. So that's going to be our crust up there. Now think about the scales involved here. When we're compare that entire planet with a radius of 6,370 something kilometers to the center. Let's compare that to a watermelon. So I think my watermelon here is going to be 30 centimeters in diameter. So 40 kilometers out of this 6,370 kilometers, that's not like the rind of the watermelon. That's too thick. So zoom in even further, and we're talking about just the area right at the edge of the watermelon, where if you were to take a knife and peel that, you can peel back just that little thin green skin. That's the scale that we're talking about, would be 1 millimeter into our watermelon. So the crust. So we're already considering the idea that denser materials, or things that are more affected by gravitational sedimentation, are going to migrate towards the core, while things that are not are going to be left enriched in this crust material that we're talking about. So there is differentiation in the mantle crust differentiation as well. There's another important set of terms to give you here: siderophile and lithophile. These are the only two we're going to worry about, but there are atmophile and chalcophile and various phile elements, but really we only want to talk about the siderophile and the lithophile, meaning iron-loving and earth-loving or silica-loving here. So siderophile elements are iron, of course, and then other things that you might think of as going with it. Cobalt, nickel, stuff like platinum and gold, those are siderophile, and they tend to be enriched further in planet towards the core. Lithophile elements, silicon obviously by definition, but also most of the things over on the group 1 and 2 of the periodic table, your calciums and magnesiums, potassiums, sodium, stuff like that. But then some odd things happen, preferentially fractionating into the crust as well, like uranium. So the crust is this very thin outermost layer of the planet. It's a very small fraction of the overall picture of our planet. However, it's the only part of the planet that humans have ever gotten to observe directly. So that's mostly what we know about directly. Everything else, we try to create models and hypothesize our best guess as to what's going on down there. Also important to note that we're going to talk about two major types of crust: oceanic crust and continental crust, and lumping them. So that distinction of oceanic and continental crust is mostly about the type of minerals involved. The oceanic crust is made of denser mafic minerals, and we'll talk about that term when we get to the igneous rock stuff. And it tends to lie denser in the crust or denser in the mantle, I should say, instead of the crust. It lies denser in the mantle. It sinks a little lower because it's denser. And then remember that the oceanic crust is going to be somewhat thinner than continental crust. We'll get to that one in a second. So oceanic crust is typically 5 to 10 kilometers thick, and it's also covered by ocean typically, so it's down to like 15 kilometers below sea level. There's usually a thick layer of sediment. Then you have these layers of basalt. So we'll get to igneous rocks and what basalt means, but for now think of it as the solidified magma you might see in Hawaii. Then below that is another type of igneous rock called gabbro, which is an intrusive type, And again, we'll get to that in the igneous rocks lecture, but you have these, and then I got a little ahead of myself in that last slide, so catching back up. So that was oceanic crust, and now we're going to talk about continental crust here. Continental crust is significantly thicker, and it's also significantly more complicated than oceanic crust. We're not going to get into all the detail on this and how it differentiates, and how you have these different kinds of structures that typify continental crust. Just think of it as thicker and also less dense, and that's going to be important when we talk about plate tectonics. So it's usually quite a bit thicker, about 30 to 40 kilometers, maybe really thick like 60 kilometers in some of the big mountain ranges. And then, now I think this is where I was trying to get at the end of the last slide. Now we're going to get to the very bottom. This bottom that we're about to talk about would be a bottom for the continental, also for the, it is called the, and I'm going to try with the name, Mohorovicic discontinuity. It's not great to try to say, and almost everyone just says Moho because that's the usual abbreviation for it. Here's the guy's actual name, and he's the one that proposed it. Basically what happens is when you're watching earthquake waves, which we'll talk about later, their speeds and their directions change dramatically when they hit this Moho layer. And so we talk about it being discontinuous in terms of wave velocities. Now, there are other discontinuities in the system from that table we saw much earlier, but this is the one that's most talked about. And it marks the transition from the crust to the upper mantle.